Spring break. This is the last lecture before exam 2. So we've got a few things to cover, but actually not a lot in this video. So reminder, chapter 5 is out there. That's the one remaining homework assignment. You can definitely see me during office hours to talk about any of this material, do practice problems. What you do need to know is quiz 3 will open on Monday after office hour, and then it's open till Wednesday. So you have the window, April 6th, April 8th, and the time is on Canvas, so you can see what that window is. Once you open the quiz, you have 1 hour. So be prepared for that, ready to go, 1 hour for quiz 3. Exam 2 then is going to follow a very similar format. It's going to be 2 hours though. It'll be open from April 8th to April 10th. Just like before, you're going to have a multiple choice section, and it'll have a short answer section like exam 1. So that'll look very much the same. Today there's 2 main topics we're talking about. There'll be some good review as well, but we're going to be looking at Vesper theory and then how shape determines polarity. So this week, chapter 5, part 2, and exam 2, that's the schedule. And don't forget, this quiz 3 is also here on April 6th through the 8th. So what this is the valence shell electron pair repulsion theory. It's just a mouthful. It sounds great. You can tell your friends, family, the Vesper theory. That's what you're talking about and understanding. And if you look at the words, it's electrons. Okay, electrons are negative, so of course they're going to repel. So it's a really basic theory to tell us about geometry. What do these molecules look like? In order to understand that, we know that electrons want to fully separate. If they fully separate, get away from each other, that's the minimum amount of energy. So that's the structure of the molecule. So we'll go through several examples to see that. Couple things, we're going to start with the review. This will be a nice geometry review. Maybe that's high school math. Circle has 360 degrees. So if we're thinking about molecules then, we keep that in mind. If we have a central atom and we have atoms on the end that want to get as far away from each other as possible, they would look like this. So that's a linear arrangement. That means linear has 180 degrees separated between this atom and this atom. We continue with our circle theme, and we have 3 atoms now on the outside and a central atom. So that's the full circle, 360. Now if divided by 3, that's where we get this 120 degrees. Okay, if we had 4 in a circle, and actually this shape doesn't occur until CHEM200, but it's a good reference point. If you have 4 in a circle, that takes us to 90 degrees. Okay, well, sorry, this occurs a lot in CHEM201. It occurs just briefly here in CHEM200. I'll talk about this shape of CHEM200 topic of 4 outside atoms. Usually we associate, and you may recall this from Chem 152, 4 associated with 109.5 degrees. That's that tetrahedral shape. So Chem 201, you'll see structures that take this primarily. Here we're usually with tetrahedral. So talk a little bit about that. One other thing is we'll talk about planes of atoms. So if we have a plane of atoms in this plane, and then if we intersect that with another plane, the angle between these 2 planes is 90 degrees. So that'll be important to know when we're looking at more complicated shapes. So some of the shapes will be reviewed from Chem 152, and then we're adding some shapes on top of that. So this is a reminder, electrons, that's what those dots mean. They repel, they want to get as far away from each other as possible. So we need to go back, do we have a good Lewis structure? How many electrons are where? And then how are they going to repel? So our electron groups, you can see here, that's a single bond, a single bond, a single bond. But actually electron groups can be single bond, double bond, triple bond, could be a lone pair, could be a single electron. So any thing with an electron in it is an electron group, and that will be important terminology when we get to this later. So start with our two examples. Carbon dioxide, 2 atoms. Okay, if they're going to be separated, whether it's a lone double bond, single bond, those are electron groups. That's 180 degrees. This beryllium compound, you can see here again, single bonds, 2 atoms, 180 degrees. So if we have no lone pair and we have 2 atoms, that's going to have a linear arrangement. So the shape is linear, and we'll also think about what the electrons are doing. The electron geometry or electron shape, that is also linear. So we'll emphasize 2 things: electron geometry and a molecular geometry. And right now, because there's no lone pairs, the electron geometry and the molecular geometry are the same. In this case, linear. Okay, now if we look here, this is trigonal planar, so that means we've got 3 electron regions. And remember, in a circle, they want to separate out. That's to 120 degrees. So this boron trifluoride, that's 120 degrees separating each of those bonds made up of single bonds. If we look over here, we can see not all electron regions are the same. That's a double bond. This is a single bond. This is a single bond. So this is taking up more space. So you can see it's squishing down, squishing down. So this is less than 120. This is actually greater than 120, okay? But the general shape, trigonal planar, that's the shape of the electron geometry and molecular geometry when we have central atom surrounded by three atoms. Mentioned earlier the tetrahedral, it's this magical 109.5, maybe you recall that from Chem 152. You can see 109.5 gives us more space than if we did 4 in a circle. Remember, that's 9 degrees, so that would be closer to each other. That's why we have this tetrahedral arrangement. So 4 atoms surrounded by a central, or a central surrounded by 4 atoms. That's electron geometry, molecular geometry of tetrahedral. Now we get to new shapes. Okay, so you can see some of these words are going to be repeated, trigonal or pyramidal. So you have to be really clear on what shape are you talking about. Okay, so here, now we get up to 5 electron regions. And if you take a look here, we've got 2 regions that are called axial, and we've got 3 regions that are called equatorial. This is really important to note that there's 2 different angles between these, okay? So there's 120 with the equatorials because that's a trigonal planar right there. And then remember, this is a plane, and started out, this is the geometry as well. This is a plane, and then this is a plane. Those intersect, that's that 90 degrees here, okay? So 90 and 120, depending on which one we're talking about. So this terminology, equatorial, the equator, axial is above or below the equator here, and that's trigonal bipyramidal, 5 electron regions. So that's the electron geometry and molecular geometry of trigonal bipyramidal. So take a look here. We do not have a difference of this axial and equatorial. You can see these are all 90 degrees, so these are all the same. Okay, and I encourage you to think about this with model kits. See me during office hours, I can show you the model kits. But this arrangement, they're all the same. You can rotate it, and they're all the same atoms, 9 degrees apart. And the name is octahedral. So that's 6 atoms surrounding. So the electron geometry, molecular geometry is octahedral. So this is the last one of all of them being the same, electron geometry and molecular geometry. Now we're going to add in lone pairs to this to see some other shapes that can be added. First I want to point out lone pairs. Okay, so I mentioned earlier a single bond, double bond aren't the same in terms of taking up space. That's the same with a bonding pair and a lone pair. Look how this lone pair really spreads out. The bond keeps the electron region in between these two, so that takes up a different amount of space. So this is what we're focusing on now, is what happens when we add these lone pairs to these shapes. What's the structure, and then what's the angles. So you can see repulsion, lone pairs has the greatest repulsion because they're taking up all this space, then lone pair, bonding pair, and then lastly bonding pair, bonding pair. So let's look at an example, okay? Trigonal pyramidal, well, where does that come from? Well, the electron geometry is what we start with. You can see that's 1, 2, 3, 4 electron regions, and you may recall that's tetrahedral. But because one of these electron regions is a lone pair, that changes the molecular geometry to this trigonal pyramidal. Okay, so trigonal, there's 3 coming off, and there's nothing up top here. There's no atom, there's a lone pair, so that has a pyramid shape coming down. Okay, so that's trigonal pyramidal from this electron geometry of 4, but only bonding to 3 atoms. So we mentioned the lone pair takes up more space. Well, in this case, the lone pair is taking up more space. You can see now it's actually less than 109.5. Okay, so the good news in this chapter, you don't need to know specific bond angles of 107, 102, anything like this. Of these special shapes, you need to know the bond angles for all the general shapes. And then you can go from there and say, well, if this is a lone pair and it was tetrahedral, it's going to be less than 109.5. That's the predicted molecular geometry. If we do this again, we can say the electron geometry here is 4 electron regions, and that's another tetrahedral. And then the molecular geometry, because now there's 2 lone pairs here and here, that takes this bent shape. Okay, so molecular geometry bent, electron geometry tetrahedral. That's the key terminology, because the question will be asked, what's the electron geometry? What's the molecular geometry? And again, you can see lone pair takes up space, lone pair takes up space. So this is even more of an effect. So we said less than 109.5 for ammonia, now even less than that for 109.5, but for our cases, as long as it's knowing that this is the tetrahedral geometry, 109.5, there's lone pairs, so it should be less than 109.5. All right, so we get now to the little more complex. So remember our electron geometry. We want to think about electron regions. And we can see here, that's 5 electron regions. Okay, so the 5 electron regions, that's the trigonal bipyramidal. So what's important to note here, as you recall, remember there was equatorial and there was axial. So remember the axial is 90 degrees from all of these atoms. So if you have 2 90-degree lone pairs bonding, that's a greater repulsion. Okay, so what we're saying is that the lone pair are not going to go in the axial position. The lone pair are going to go in the equatorial position. So it gives this real odd looking shape of seesaw. So electron geometry, trigonal bipyramidal, molecular geometry with 1 lone pair goes in the equatorial, it gives you seesaw. Okay, so it does not over here go in the axial position. So we can continue that. Electron geometry, 5, that's trigonal bipyramidal. Now we have 2 lone pairs to get to our molecular geometry. That's 1, 2, and remember they're in the equatorial position. Axial position stays. And now this is a pretty distinct looking shape. If you turn your head over, you can see that's definitely lives up to its name, a T-shaped molecular geometry T-shape. We're not done yet. So electron geometry, still working with the trigonal bipyramidal that has 5. In this case though, we've got 1, 2, 3 lone pairs all in the equatorial position, and you can see now we're left with this a linear molecular geometry here. We've got 1 electron geometry left, so that's our octahedral. So that's the one with 6 electron regions. That's our octahedral. You can see down here, octahedral. And remember, I tried to emphasize before, there's not an axial or equatorial position. All of these are the same. So the fact that the lone pair was drawn here at the bottom doesn't mean anything. That lone pair could have been here, could have been here, could have been here, doesn't matter. But we just show it here at the bottom in this case, and now if you take a look, that's flat. So that's where this name comes from, square pyramidal. That's our molecular geometry. So again, quiz questions, homework, exam. What's the electron geometry? Octahedral. What's the molecular geometry? Square pyramidal. And one thing to note here, if we're in an octahedral still, and we said, well, we took one away from the bottom, what you want to know is that the next lone pair is going to go as far away from it as possible. Remember, the lone pairs take up a lot of space, so they're opposite of each other. If they're opposite of each other, now you can see, this is where I gave the intro, if this was 4 atoms in one plane, that's that 90 degrees. It's very unique here with the octahedral electron geometry, okay, and that's called square planar. Like I said, this occurs quite a bit in CHEM200 and other special class of compounds, but typically when we think of 4 atoms surrounding a central, we think of tetrahedral 109.5, but that's not accounting for the lone pair that are over here. So in this case, lone pair, opposite sides, that's 90 degrees, square planar. All right, so quick check. Go ahead and pause, see if you can predict the geometry of these 2 examples. A couple things to note. This is a great review for Lewis structures. So if we review, that's 4 valence electrons for silicon, 7 times 5 for fluorine. We've got a charge, so that's +1. So we've got 40 valence electrons here. So now you can see definitely different Lewis structures than CHEM152. Maybe you did this in CHEM152. My classes would not, but this is expanded octet, and you can see now I'm even drawing it a little bit like the shapes that we've talked about, this trigonal bipyramidal. So if I've got 8 valence electrons on each of these fluorines, that gives me a total of 4. So we're all set here. So if it has 5 electron regions, so the electron geometry is trigonal bipyramidal. And because there's no lone pairs, the molecular geometry is also trigonal bipyramidal. So that's this one, and don't forget if this is a Lewis structure of an ion, brackets, and then the charge. The sulfite is a little bit different. I want to do this one because it's actually really good practice for an exam coming up. If I put in the number of valence electrons, we can see that's total of 26. And thing to note here is remember to use formal charge. So formal charge is a guide to help with your Lewis structures, because maybe you drew this structure, you drew out and you have enough electrons, so everyone gets their octet, life is good, and great. That's sulfite. Well, if you do the formal charge of these, things look a little bit different. So I'll let you calculate the formal charge, but if you take a look here, that would be -1 for all of these oxygens, and +1 for the sulfur in this structure. Remember, just like what we did up here, expanded octet, you can expand the octet here. And we can always check with formal charge to see, is this any better of a structure? Okay, so here, lower structure, and double check the formal charge of these two oxygens. If you take a look, that's going to be -1, -1. The formal charge of this oxygen, so that's 2 lone pairs, 2 lone pairs, half of the bonding ones, valence electrons is 6, so that's a formal charge of 0. And if you take a look, sulfur has 6 valence electrons, that's a formal charge of 0. So remember our rules for formal charge, lower the numbers, the better. 0, 0, -1, -1, this is higher numbers. And when we have a negative number, that should be on the more electronegative. So that's true, that's the case here. So this is actually a better Lewis structure than this. And then it goes up to the question of geometry. Well, we have 1, 2, 3, and now it's a double bond, but it's still an electron region. And there's 4, a lone pair. So the electron geometry is tetrahedral. But this question is asking about the molecular geometry, and that's that trigonal pyramidal. Okay, so if you take a look, we had trigonal bipyramidal up here, and trigonal pyramidal. So you definitely want to be clear with your notation here. I made this for the sake of writing out the names, but that's trigonal pyramidal, that's trigonal bipyramidal. All right, so to review, what I want you to take home from this table is there's an electron geometry and there's a molecular geometry. Okay, so if we look at that, linear, only options are to be linear. Then you want to note, what's the angle? Well, linear, we said that's 180 degrees. Then you look, the next one has 3 electron groups. And if it has no lone pairs, that's the standard shape that we looked at, you can see that the electron geometry and the molecular geometry are the same. Okay, that's our 120. But if we have 3 electron groups and we have 1 lone pair, the electron geometry is still trigonoplanar, but now the molecular geometry is bent. So this is another example, we didn't do this one, SO2, and again, because that lone pair up here, it decreases the angle 120. Tetrahedral is the electron group of 4, and the lone pairs, that gave you trigonal pyramidal and bent shape. So all of these are Chem 152 shapes. So my classes in Chem 152 would know all these shapes, know the angles. What we've added is the next slide in Chem 200. So we go from 4 electron regions to now 5 and 6. So the new terms were, we had trigonal bipyramidal. If we have a lone pair, 1 lone pair, then we have seesaw. 2 lone pairs, T-shaped. 3 lone pairs, linear. The next one, 6 electron groups or 6 electron regions. That gives us octahedral. Then if you have 1 lone pair, that's square pyramidal. You can see at the bottom, now these are a pyramid. And then 2 lone pairs, that would be the opposite of each other. That's the square planar. So really important, square, square, pyramidal, bipyramidal. You need to be really clear when you're identifying shapes. What shape are you talking about? What are you trying to label it as? So this is good practice. Again, see me during office hours. You want to look at models. You want to talk about these shapes, angles, all of this. We can do that during office hours. Some of you are going to start practicing drawing, and we'll spend a lot of detail on drawing these molecules with good representation. What I mean by that is you can see there's a dash or a hatched wedge, a solid wedge. It's trying to give you spatial arrangement here. So you can see those are on a plane. One's coming out, one's going back. Same thing here, 2 are going back. two are coming out towards you. So this is to give you some perspective. Tetrahedral is a really common one, again, coming out, going back. So that could help as you're practicing drawing these. If it's a straight line, that's in the plane of the paper. The others are coming out or going back. So what you've just done then is the foundation for any molecules. Okay, so you go into biochemistry, biology, the molecules get bigger and bigger and more complicated, but guess what? These are just central atoms. So if you take a look, this is an amino acid, glycine, simplest amino acid. Nitrogen has 1, 2, 3, 4 electron regions. It's got one lone pair, so this is trigonal pyramidal here. If you look at this carbon, it's got 1, 2, 3, 4 electron regions, no lone pairs. That's tetrahedral. This carbon has 1, 2, 3 electron regions. That's trigonal planar. And this oxygen, 4 electron regions and 2 lone pairs. That's bent. So the more and more complicated molecules you get, you just have to focus in on what's the central atom, how many bonds, how many lone pairs, and then know your shapes. So this will definitely carry on as you continue in the sciences. And now you can see it, trigonal pyramidal, it has that shape right here. Tetrahedral has that shape. Trigonal planar, you can see that's all in one plane. And then you've got definitely that clear bent shape. So I encourage you practice. You can practice with toothpicks, marshmallows. If you have model kits, you can really practice and see this. That'll be the problem if you're not on campus doing this in lab, is you don't get to see the model, see the shapes. There's some good programs also to build molecules and get shapes if you want to simulate. You can do that. So the last topic that we're going to end up on is the theme of this book, structure. What's the shape of the molecule? Determines properties. Is the molecule polar or not? So this is a really big emphasis of this text. Structure determines properties. So here, what do you got to do? Draw a good Lewis structure. You got a good Lewis structure, then you can just go through all the shapes that we did and determine the molecular geometry. Now we need to go back to the beginning of this chapter and say, wait a minute, what's the difference in electronegativity? Is it a polar or non-polar bond? And remember that threshold is this 0.4. Is it polar, is it non-polar when you subtract the two electronegativities? And lastly, do these polar bonds cancel or do they give a net dipole? We talked about a dipole is something that can be measured. So we're trying to determine, can we look at this molecule, look at the shape and say, yes, it will have a dipole that can be measured, or no, there's no net dipole. All right, so this is physics. Taking vectors, adding, subtracting. If you take a look here, we've got a linear molecule, and this is assuming that the atoms are the same on the end. So let's say it's pulling this direction, it's pulling this direction. That cancels and makes it nonpolar. That's a linear arrangement with polar bonds that are the same in opposite directions. In this case, bent, you can see the molecule is pulling this direction. Molecule's pulling a little off that direction. There's nothing pulling this way to cancel it, so there's a net dipole here. That's a polar molecule. Trigonal planar. You could separate these vectors into right and down, left and down. I'm trying to draw them the same, but if you did that, it would all cancel, and that's a nonpolar molecule. Same thing here for tetrahedral. It's a little more complicated, but if you drew all these vectors out in the arrangements, they would cancel and give you a nonpolar. However, if you put a lone pair up here, then nothing's pulling up. We're missing that piece. So overall, then this is polar because it can be pulling down. So what we're talking about then is this net dipole that we saw in previous video. there's more electron density region in one area than another. So this is a partial negative, this is a partial positive. You can see a positive arrow on one end, the arrow pointing to the more electronegative on the other. This is always to represent a polar bond and then a net dipole. So you can see here, carbon dioxide, this is a polar bond pulling this way, polar bond pulling this way. Because they're the same, cancels out. No net dipole. You can see, look how uniform this electron region is. So this is a nonpolar molecule. For water, on the other hand, you can see the partial negative is showing where the poles are being pulled. So the more electron region density here, less here, and this is the partial positive region. The hydrogens, the electrons are being pulled away. So that's the partial positive. So this is a polar molecule. Okay, so the real important distinction here is there's a difference between bonds and molecules. So first, if we look, this has polar bonds, but it's a nonpolar molecule because it cancels. This one has polar bonds, they don't cancel, that's a polar molecule. So do a couple here. Take a look again, a good review. Lewis structures, nitrogen 5, oxygen 6, 7, that's a total of 18. And the least electronegative is the central, that would be oxygen. And you can use formal charge again to determine where a double bond should go, but the double bond is going to go towards the oxygen. And then you can count up 2, 4, 6, 8, 10, 12, 14, 16, that's 18 electrons. That's good. Okay, but now we need to know about the bonds. So nitrogen, oxygen, electronegativity of 3, of 3.5. So this has a difference of 0.5. If we do chlorine now, 3, and chlorine's also 3. So we have a nonpolar bond over here, but we have a polar bond. So I'm indicating this with the arrow pointing to the more electronegative, the positive remaining on the least electronegative. So you can see then overall, if I think about the shape, now I can draw the shape. That's bent. And we have a net dipole in that area, so this would be overall a polar molecule. Then our other example, SO3, we saw this sulfur-oxygen combination earlier with sulfite can give you some interesting Lewis structures. Same thing here, we can expand the octet. Remember, this is period 3 or lower, and we've got a Lewis structure here. And if you look up the electronegativity values, we already said oxygen's 3.5 and sulfur is 2.5. So this is definitely a polar bond, but the polar bond is going this direction, and you can see 3 electron regions, trigonal planar. So those 3 are canceling out. So this is a nonpolar molecule. So if we take a look, polar has the bent geometry that we drew here, and then SO3 is nonpolar because it has a trigonal planar geometry, and those cancel out. So you can see just because you know, it's trigonal, it's bent, you have to think about the bond. Is the bond polar or is the bond nonpolar? So start there. That tells you, is the molecule polar? And then polarity tells you about properties. So maybe you know this, oil is nonpolar, water is polar. They do not mix. Structure determines properties. That's what we find out from that.